Let's find the quadratic function y equals ax squared plus bx plus c, whose graph passes through the points 1, 4, 2, 1, and 3, 4. So 1, 4, 2, 1, and 3, 4 are all x's and y's, pairs of x's and y's. So let's start by plugging in each of these points separately to get three different equations. Plugging in 1, 4, we square the 1 to get 1. 1 times a is a, 1 times b is b. Y was 4, so 4 equals a plus b plus c. Let's do it again with the second point. X is 2, y is 1. Square the 2 to get 4, 4a plus 2b plus c. 1 equals 4a plus 2b plus c. You see where we're going with this. Let's go ahead and substitute the third pair. The 3 for x, the 4 for y. 3 squared is 9, so 9a plus 3b plus c equals 4. We've now got three equations with three unknowns. Instead of x, y, and z, the unknowns are a, b, and c. I bet you didn't see that coming when we started with y and x in the original equation. So we're going to take these three equations and we're going to solve the system. Let's go ahead and eliminate c from equations 1 and 2. We don't have to start with that. You could start by eliminating c from equations 2 and 3. Or you can try to eliminate b or try to eliminate a. I just like the fact that all three of them have plus c. That means that the most I'm going to have to do to change the equation to get rid of c is multiply by -1. So to eliminate c from equations 1 and 2, I'll start by multiplying equation 2 by -1. But again, I didn't have to do that. I could have done it to equation 1. All roads lead to the same solution, as long as we're doing correct things. So multiplying that second equation by -1, it turns it into -4a minus 2b minus c equals -1. Now, if we add these two equations together, the c's go away. We're left with -3a minus b equals 3. Let's put that aside and eliminate c from equations 1 and 3. We didn't have to do 1 and 3. We did 1 and 2. We could have done 2 and 3. All roads lead to the same correct answer. I'm going to do 1 and 3. And I'm going to multiply the third equation by -1. Which will change my signs. I'll add them together and I'll get -8a minus 2b equals 0. I've given myself a system. I can multiply equation 1 by -2, the 2 to match the 2b on the bottom, the negative to change the negative to positive to counteract the negative on the bottom. But that'll give me my plus 2b. It'll also give me a positive 6a and a -6. When I add these two equations together, I'm going to get -2a equals -6. I'm going to divide both sides by -2. Negative 6 divided by negative 2 is positive 3. I have my A. I'll back substitute into one of these two equations. I have negative 3a minus b equals 3 here. Plugging in that 3. That's negative 9 minus b equals 3. Add 9 to both sides. We'll get negative b equals 12, which means the opposite of that. B equals the opposite of that, negative 12. So from negative b equals positive 12 to b equals negative 12. Now we have a equals 3, b equals negative 12. Let's plug those in to one of our original ones. I'm going to pick the one that is the simplest looking. We get 3 minus 12 plus c equals 4. 3 minus 12 is negative 9. So negative 9 plus c equals 4. Add 9 to both sides. C equals 13. So we found that a equals 3, b equals negative 12, and c equals 13. That means that the quadratic function whose graph passes through those three given points, remember we found a, b, and c of a quadratic equation, y equals 3x squared minus 12x plus 13. And that's it for this topic.
3 variables. Now, we're not going to talk about solving this graphically because 3 variables requires 3 equations, and you might have noticed the graphs we've been dealing with have an x-axis, a y-axis. Do you know where the z-axis is in this case? Let me tilt this. It's coming out at you. It's going straight through. Straight through. Or maybe picture it like this. There's a third one coming straight down through it. These are all right angles. All right angles. When we're talking about 3 intersections, it looks like that. A single solution. So top left would be a single solution. Second one on the top would be the points in common form a line. Bottom left, bottom right, bottom middle ones. All the ones along the bottom are examples of no points in common. Yeah, we're not going to talk about solving these graphically. Let's take a look at example 6. We have 3x plus 9y plus 6z equals 3. 2x plus y minus z equals 2. And x plus y plus z equals 2. 3 equations, 3 unknowns. So our steps here, we know how to solve things that have 2 variables. We know how to take 2 equations, 2 unknowns, and solve the system. So let's do that. We're going to take 2 equations. We're going to pick ones where it would be easy to just use our elimination method to get rid of one of the 3 variables. And that will leave us with a new equation, not 2, one new equation that only has 2 variables. Then we're going to pick 2 more equations and eliminate that same variable. Create another equation that only has the 2 variables in it. And then we're going to solve that. We'll get 2 of our variables, we'll plug it into one of the equations and solve for the third. I hope you followed that. Now, let's go to work. I'm going to take these 2 equations right here. Why? Because notice, negative z, positive z. I could eliminate that right away. So 2x plus y minus z equals 2. X plus y plus z equals 2. If I add down, that z is gone. 3x plus 2y equals 4. That's one of the 2 equations that I'm going to create. I would like to eliminate z somewhere else, but I can't use 2 and 3 again. I've already used equation 2 and equation 3. So let's use 1 and 2. Because I want to get rid of z again, that has the plus minus. If I multiply this second equation by 6, I'll have plus 6z minus 6z. The z will go away. So I do that. 3x plus 9y plus 6z equals 3. Leave equation 1 alone. Multiply 6 through equation 2. 12x plus 6y minus 6z equals 12. Z's are eliminated. I get 15x plus 15y equals 15. This is my equation 2. So I'm going to take my new equation 1 and my new equation 2 that are just x and y. Create a new system. 3x plus 2y equals 4. 15x plus 15y equals 15. All the signs are the same. I can't easily multiply 2 to 15. I can't easily multiply 4 to 15. I can easily multiply 3 to 15. 3 times 5 is 15. But I'm going to use negative 5 because I want it to be a negative 15 so that it cancels out the positive 15. Negative 15x minus 10y equals negative 20. Leave the equation 2 alone. The x's have been eliminated. Negative 10y plus 15y is 5y. Negative 20 plus 15 is negative 5. divide both sides by 5, I get y equals -1. I'm going to plug that back into one of the original me created equations. 3x plus 2 times -1 equals 4. 3x minus 2 is 4. 3x is 6. X equals 2. But we're not done. Our original equation, our original system was x, y, and z. I like this one. This is nice and easy. X plus y plus z is 2. If x plus y plus z is 2, then 2 plus -1 plus z is 2. 2 plus -1 is 2 minus 1. 1 plus z equals 2, which means z equals 1. So, instead of an ordered pair, we would call this an ordered triplet. X, y, and z, order matters. 2, -1, 1.
We have the system 3x minus 6y plus 7z equals -13. 5y plus 2z equals 2. And 3z equals -12. Well, notice when it's set up like this third equation we can easily solve and get z right away. If 3z equals -12, then when we divide both sides by +3, we get z equals -4. And now that we know that, we can go to this one, plug in z equals -4, and easily solve for y. 5y plus 2z equals 2. That's 5y plus 2 times -4 equals 2. 5y minus 8 equals 2. Add 8 to both sides. Add 8 to both sides. 5y equals 10. Divide both sides by 5. There's y equals 2. And now that we have y and now that we have z, we can plug those into the first equation and easily get x. I need room. So far our answer is the ordered triple where y is 2 and z is -4. We just have to solve for x. I just want all this room. So 3x minus 6y plus 7z equals -13. We're going to solve for x. Y is 2. Z is -4. 3x minus 12 minus 28 equals -13. -12 minus 28 more is -40. 3x minus 40 equals -13. I'm going to add 40 to both sides. I get 3x equals +27. And from 3x equals 27, I'm going to divide both sides by 3. X equals +9. So our answer is the ordered triple where x is 9, y is 2, and z is -4. The objectives of this topic are recognize systems of nonlinear equations in two variables, solve nonlinear systems by substitution, solve nonlinear systems by addition, solve problems using systems of nonlinear equations. So now we're talking about nonlinear equations, things that don't graph as lines. So at least one equation that cannot be expressed in the form ax plus by equals c. If at least one of them can't be expressed in that form, which is a line, then we have a non-linear system. But as before, a solution is an ordered pair that satisfies both equations, and the solution set is the set of all such ordered pairs. As with linear systems in two variables, the solution of a nonlinear system corresponds to the intersection point or intersection points of the graphs of the equations in the system. So this is important to know because let's say we have a line and a circle. Well, a line's going to pass through a circle twice. We know to expect two solutions. Our solving methods are the same. I just discussed graphically. We have substitution. Here we have x squared equals y minus 1, and 4x minus y equals negative 1. That first equation having an x squared in it means it's a parabola. It is not a line. This is therefore a nonlinear system. But we can solve x squared equals y minus 1 for y. Add 1 to both sides. Y equals x squared plus 1. And then take that expression for y and plug it in to the other equation. So instead of 4x minus y equals negative 1, we have 4x minus x squared plus 1 equals negative 1. And since we were subtracting the entire y, we have to subtract the entire x squared plus 1. Let's solve this. Distribute the negative. Minus x squared minus 1. Well, we have a quadratic here. Let's get everything on one side and 0 on the other. I'd like to move my x squared to the right so that it's positive, which means I'm also going to subtract 4x. So x squared minus 4x. And then if I add 1 to both sides, that gives me the 0. So 0 equals x squared minus 4x. I can factor that. I can factor out an x. Oh no, factoring came back. Then I could use the zero product property and set each of these factors equal to 0. So x equals 0 or x minus 4 equals 0. Add 4 to both sides to get x equals 4. So I have two x values. That means that I have at least two answers. Let's plug in 0 for x. Let's also plug in 4 for x. Plugging in 0 for x. If y is x squared plus 1, then y equals 0 squared plus 1. When x is 0, y is 1. Plugging in 4 for x. If y is x squared plus 1, y is 4 squared plus 1. Y is 16 plus 1, y is 17. So when x is 4, y is 17. Thus, the points 0, 1, and 4, 17 are our proposed solutions. If we check, they do satisfy both equations. Our solution set is the set containing both of those points. Graphically, this is a line and a parabola. 2 points of intersection. So we can still use substitution. We could also still use addition as long as our two terms are like terms with each other's equation. So we see here we have an x squared and an x squared. We have a y squared and a y squared. We can line those up. Therefore, we could use the addition method. We're going to have to multiply both equations by a number here to be able to use the addition method or the elimination method, whatever you want to call it. So let's multiply the first one by 3 and the second one by -2. That's going to get rid of our y squareds, because if we multiply the first equation by 3, we're going to get a plus 6y squared. If we multiply the bottom by -2, we're going to get a minus 6y squared. It's also going to give us a 9 squared and a 105. It's going to give us a -8x squared and a -96. When we add these together, we get x squared equals 9. When we solve x squared equals 9, we get x equals plus or minus 3. So once again, we have two x values. Let's start by back substituting the positive 3. So 3 times 3 squared, or 3 times 9, 27, plus 2y squared equals 35. Subtract 27 from both sides, 2y squared equals 8. Divide both sides by 2, y squared equals 4. Take the square root of both sides, y equals plus or minus 2. So you may have noticed in the last example, I said when we had two x values, we had at least two solutions. That allowed for this possibility. We have two x values, and our first x value gave us two y's. So we have 3 positive 2 and 3 negative 2. And we still have to plug in our -3. While plugging in -3 into this equation is still going to give us 3 times 9, which is 27. Subtract the 27, divide by the 2, take the square root of the 4. We're also getting y equals plus or minus 2. But this plus or minus 2 comes with the -3 as an x. So we had 3, 2, we had 3, -2. Now we have -3, 2, and -3, -2. Our solution set has 4 points. That means there's 4 points of intersection between these two things. They aren't lines. So an application involving a system of nonlinear equations. These application problems won't apply to every application problem you might come up with, but all of these application problems that you're going to encounter are going to have the same thing in common, and that is that you can express them You can express the given situations as a system of equations, whether it's a linear system or a nonlinear system. And by solving that system, we answer the question. So here we want to find the length and width of a rectangle whose perimeter is 20 feet and whose area is 21 square feet. So perimeter is 20 feet. Perimeter is 2L plus 2W. Twice the length plus twice the width, aka the distance around. The area is 21 feet. That's length times width. So that's two equations right there. If we let x equal the length and y equal the width, then 2x plus 2y will give us 20, and x times y will give us 21. Let's go ahead and solve this system. Let's take xy equals 21. Notice we can't use elimination here because the top has an x and a y and the bottom has an xy. Those are not like terms. We can only use substitution. Solving for y, dividing both sides by x gives us y equals 21 over x. Let's plug that into the other equation. So 2x plus 2y becomes 2x plus 2, 21 over x. That's 2x plus 42 over x equals 20. Multiplying by 2 is multiplying by 2 over 1. We can get rid of the x in the bottom by multiplying by x. So let's multiply both sides of this equation by x. Distribute on the left, 2x squared. Distributing, the x's cancel, leaving us with just plus 42. And then 20 times x is 20x. Let's get everything on one side, 0 on the other. So subtract 20x from both sides. We notice we can factor a 2 out of the left. And then we can further factor x squared minus 10x plus 21 to be x minus 3 times x minus 7. Solving this, 2 equals 0. That's false. We throw that away. Or we can divide both sides by 2 and just make the 2 go away. Common thread there. Go away 2. You don't have an x, so we can't solve for you. X minus 3 equals 0, or x minus 7 equals 0, means that x equals 3, or x equals 7. So we have two values. We're going to back substitute into xy equals 21. Plugging in the 3, plugging in the 7, solving. When x is 3, y is 7, and when x is 7, y is 3. So we found two solutions. And we have to translate what that means in terms of this problem. Remember, x was the length and y was the width. So the rectangle could have a length of 3 and a width of 7, or it could have a length of 7 and a width of 3 to give us the perimeter 20 and the area 21. And those check. And that's it for this topic.
Solving a nonlinear system. It's exactly what it sounds like. It's a system of equations where at least one of the equations is nonlinear. So, A system of equations in which at least one equation is not linear is a non-linear system. So substitution is going to be your go-to in this case. So we have x squared minus y equals 4, and x plus y equals -2. We can't, I know it looks like, hey, let's use elimination, but x squared plus x is x squared plus x. We don't want to do that. So, don't want to doesn't mean you can't. Okay, let's do it that way and then use substitution. You convinced me. You convinced me. Let's see what happens. So x squared plus x is just x squared plus x, nothing more we can do. Equals 4 minus 2 is 2. X squared plus x equals 2. Get everything on one side. 0 on the other. Factor and solve. So again, I use elimination. I'm completely doing the opposite of what they say to do in example 1, but I still will come back, do substitution, show that it works, and show that it might even be better. It's not always going to be given to you like this. Numbers that multiply to -2 and add to +1. X squared, so x and x. This is going to be +2 minus 1, which gives us x equals -2 and x equals +1. We need to take both of these x's, plug them back into one of the equations, and solve for y. So, -2 plus y equals -2, but also 1 plus y equals -2. So y equals 0 when x equals -2, and when x equals 1, y equals -3. So -2, 0, and 1, -3. So that was using elimination. If you want to, again, just remember, this is not going to be 2x. X squared plus x, there's nothing you can do to that. It's just x squared plus x. Okay, let's do it again the way they asked us to. We'll see we get the same answer. So if x plus y is -2, y is -2 minus x. So x squared minus y is x squared minus -2 minus x. X squared plus 2x, or sorry, plus 2 plus x equals 4 gives us x squared plus x minus 2 equals 0. And you know what you're going to do from there? All the rest of this. Factor, solve, plug in. So you will get the same answer, because there's the rest of the work. If you didn't write it down, go back and rewind. See how we did it from that point on.
Y equals -2x squared plus 39. And x equals the square root of y. Neither of these are lines. That's why it's nonlinear. We're going to solve this using substitution. Now, one thing you can do is take this expression for y and plug it in here. The other thing you can do is take this expression for x and plug it in there, but you're going to get the same answer either way. So x is the square root of y. Let's plug that into the first one. Y equals -2. Instead of x squared, it would be the square root of y squared plus 39. And the square root of y is just y, so -2y plus 39. Add 2y to both sides, we get 3y equals 39. We get y equals 13. And x is the square root of y, which means x is the square root of 13. So our answer is the ordered pair, where x is the square root of 13 and y is 13. So that's systems of equations. A related concept is that of systems of inequalities. And I want to go over this briefly, quickly. The first thing we would have to know how to do is how to graph an inequality in the xy plane. So let's say we had 3x minus 2y is less than 6. Well, we'd pretend that we have 3x minus 2y is equal to 6, and we would graph that first. If it was greater than or equal to, less than or equal to, if the or equal to was there, we would use a solid line. But here in the case where there is no equal to, it's just less than, we're going to use a dashed line. So 3x minus 2y equals 6. We can find our x and y intercepts. When x is 0, y is -3. When y is 0, x is +2. X is 2. Y is -3. There's our dashed line. Now, to account for less than, we need to do a test, just like we did with our other inequalities. Here, the test is going to be, does this point satisfy the equation, or does it not? Or satisfy the inequality? So I'm going to pick this point right here, 0, 0, clearly on this side of the dashed line. I'm going to plug 0, 0 in. Is it true? 0 minus 0 less than 6, 0 less than 6, absolutely true. So 0, 0 is part of the side that works. So we shade that side of the line. X is less than or equal to -1. Well, just like we would do on a number line, there's -1 on the X. But instead of just shading this and doing a solid circle or a square bracket to indicate that -1 exists or that -1 works, we put our dashed line, which since the or equal to is there is not dashed, it's actually a solid line matching up with what would have been a filled in circle. And instead of just shading on the x-axis on the number line, when we're on the xy plane, we shade everything to the left, everywhere that x is less than or equal to -1. Likewise, what if we had y is greater than 3? Well, we find y equals 3. It's a dashed line because there's no or equal to, and everywhere where y is greater than 3 would get shaded. Okay. Now, what if we had the system of inequalities? (3x minus 2y is less than 6). X is less than or equal to -1. Y is greater than 3. We would solve this graphically. 3x minus 2y is less than 6. We saw was this inequality. The side with 0, 0 was included, so we shaded above. We graphed that one. Now let's graph this one. We saw where -1 was. It was a solid line. We shaded everything to the left. Notice some of it's overlapping. Y is greater than 3. We shaded everything above. Only the parts I really made a mess of this, huh? There we go. Only the parts that overlap all three are the solution to the system of inequalities. So I made a mess of that by trying to do all three at once. But let's say we have a system of nonlinear inequalities. Y is less than or equal to negative x squared plus 4. X minus y is greater than or equal to negative 2. Y is greater than negative 5. This one is an upside down parabola moved up 4. The shading is on the inside. This one is a line shaded down here. And this one is shaded up through. Well, only the part above that line and inside the parabola would make it into the final answer. So it's almost like we have this weird shape here. The intersection of all three shaded regions. So that's what a system of inequalities is and how we would deal with that. The objectives of this topic are graph a linear inequality in two variables, graph a nonlinear inequality in two variables, use mathematical models involving linear inequalities, graph a system of inequalities. Equations in the form ax plus by equals c are straight lines when graphed. We know this. If we change the symbol equals to one of the inequality symbols, greater than, less than, greater than or equal to, or less than or equal to, we obtain a linear inequality in two variables. A solution means that when we substitute the x coordinate for x and the y coordinate for y in the inequality, we obtain a true statement. So that sounds very similar to linear equations in two variables. How this is going to be different is instead of testing to see if it's on the line, we're testing to see if it's in the region or the half plane when we're talking about a line. So the graph of an inequality in two variables is the set of all points whose coordinates satisfy the inequality. Just like when we looked at polynomial inequalities and rational inequalities, and we picked a test point, and anything in that interval had the same sign, positive or negative. Here, we're going to pick a test point on one side of the line or the other. We're going to see if that's true, and if it's true, it's going to be true for everything on that side of the line. If we have an or equal to, then the line we draw is going to be solid. If we don't, if we have a strictly less than or a strictly greater than, then we do a dashed line. The dashed line means that we're not equal to. The solid line means that we can be equal to. Like I said, we're going to choose a test point. We're going to substitute that in. We're going to see if it's true. And if it is, then we shade the side containing the test point. If it's false, we shade the other side. But that means we need to go back and revisit graphing lines from the very beginning of the course. We need to be able to know how to do that in order to graph the inequalities. So here we have 4x minus 2y is greater than or equal to 8. Let's pretend that that is just a plain old equal sign and graph that line. We can do this by finding the intercepts. Plug in 0 for x to find the y-intercept. Plug in 0 for y to find the x-intercept. When y is 0, that term goes away and we get 4x equals 8. We get x equals positive 2. So 2, 0 is 1 point. When we plug 0 in for x, the first term goes away. We get negative 2y equals 8. Divide both sides by negative 2, we get y equals negative 4. So 0, negative 4 is a point. We only need 2 points to draw a line. We had an or equal to, so the line we draw will be solid through the x-intercept of 2 and the y-intercept of negative 4. Now let's pick a test point. And I love picking 0, 0, just like I liked picking 0 when we did the other inequalities. Zeros are nice and easy to plug in. When we plug 0 in for x and y, we get 0 minus 0 is greater than or equal to 8. 0 greater than or equal to 8 is a false statement, so we shade the other side. And that is our solution. Now, some inequalities we can graph without using test points, specifically vertical lines and horizontal lines. Vertical lines just think of it as an IMAX screen for the normal number line. X is greater than 3 on the normal number line would be to the right of 3. So instead of just shading the line, we shade above and below as well. Greater than would clearly be to the right, less than would clearly be to the left because there's no slant to the vertical line x equals a. And then using that same logic with greater than being up and less than being down, there's no slant to a horizontal line. No slant, zero slope to y equals b. So y greater than b would be up. Y less than b would be down. So A, let's graph y is greater than 1. There's no or equal to, so that is a dashed line. Y equals 1 strikes the y-axis at 1. That's a horizontal line. So we do a horizontal dashed line at y equals 1. And then we want greater than that. Greater than is above. So we shade up. We can only do that because there was no slant. Otherwise, we would have had to do test points. X is less than or equal to -2. We have the or equal to, so this one's going to be a solid line. X equals -2 strikes the x-axis at -2. That's a vertical line. And then less than is left. So a solid line at x equals -2, shade to the left. We graph a nonlinear inequality similarly. We replace the inequality with an equal sign, and then we graph the nonlinear equation. Here we have x squared plus y squared equals 16. This is a circle. Going back to the beginning again. So we've needed unit 1, now we need unit 2, so to speak. This is a great capstone for everything we've done so far in the course. Uses a little bit of everything. This is a circle with the center at the origin with a radius of 4. The circle is solid because of the or equal to. And now we'll use a test point. Let's pick 0, 0. That would give us 0 plus 0 is greater than or equal to 16, which is false. So we're going to shade outside the circle. Had we gotten a true statement, we would shade inside the circle. If X represents the age of a child and Y represents the awake heart rate in beats per minute, the normal heart rate region can be described by the following system of linear inequalities. X plus Y greater than or equal to 70, 2.6x plus Y less than or equal to 115. Show that point B, 690, is a solution of the system of inequalities that describes normal awake heart rate. So to show that it's a solution, we would have to plug 6 in for X and 90 in for Y, and show that X plus Y, 6 plus 90, is greater than or equal to 70. Well, that's very quickly 96. That is greater than or equal to 70. And that 2.6x, 2.6 times 6 plus 90 is less than or equal to 115. Let me just pull out my calculator. 2.6 times 6 is 15.6 plus 90 is 105.6. That is less than or equal to 115. So it is a solution. Like I said, both of those are true. Thus, it is a solution for the system. Now, let's graph a system of linear inequalities. So similar to graphing regular inequalities, the answer is going to be about the shading. But since one linear inequality shades one direction and the other linear inequality is going to shade in another direction entirely, at some point those two shadings are going to overlap, and the overlapping region is the solution set to the system. So going back to the application of the system of inequalities, just checking to see if a solution holds, this 0.690 is just one thing in the region that overlaps between these two inequalities. We want to find the graphs of the entire regions. That's what we're going to do here when we graph the solution set of the system x minus 3y is less than 6 and 2x plus 3y is greater than or equal to negative 6. We need to graph both of these. X minus 3y less than 6 will be a dotted dashed line. 2x plus 3y greater than or equal to negative 6 will be a solid line. That's because the first one doesn't have the or equal to and the second one does. Let's find the intercepts. For x minus 3y equals 6, plug in 0 for y. That makes the second term go away. We just get x equals 6. So 6, 0, an x-intercept of 6. The x-intercept for 2x plus 3y equals negative 6. Plug 0 in for y. Makes the second term go away. We get 2x equals negative 6, which gives us x equals negative 3. For y-intercepts in the first equation, plug 0 in for x. That makes the first term go away. Negative 3y equals 6 means y is negative 2. And for the second, 2x plus 3y equals negative 6, plugging 0 in for x. Makes the first term go away. 3y equals negative 6. Y also equals negative 2. So, our dashed line has an x-intercept of 6 and a y-intercept of negative 2. Our solid line has an x-intercept of negative 3 and a y-intercept of negative 2. Now we need to find the shadings. Let's use the test point 0, 0, and let's use that test point for both. Because we can, because it doesn't fall on one of the lines. If it did, we would have to pick a different test point, and we would have to learn to be okay with that. For our dashed line, plugging in 0, 0 gives us 0 less than 6, which is true. So the dashed line gets shading on the side with the origin. Our solid line, plugging in 0, 0, gives us 0 greater than or equal to -6. That is false. So the solid line gets shading on the other side. Sorry, that's true. 0 greater than or equal to -6 is true. So we get shading on the side with the origin. I was bound to screw up eventually. I'm doing a lot of this in my head, just seconds before it shows up on the screen. Now, where these two overlap, the region that's now green, that is the intersection, that is the solution of the system. So what we did with two lines with a system of linear inequalities is the same thing that we're going to do with a system of nonlinear inequalities. Graph them both, shade them both. Where it overlaps is the solution. So this is y equals x squared minus 4 when we graph it. And it's going to be a solid line because of the or equal to. This is just the standard parabola moved down 4 units. Zero, zero will give us 0 greater than or equal to -4, which is true. So we shade the part of the parabola that has 0, 0, and that's the interior. X plus y less than or equal to 2, x plus y equals 2 is a line. X-intercept and y-intercept are both 2. Solid line because of the or equal to. Plugging in 0, 0, that gives us 0 less than or equal to 2. That's true. Shade the side with the origin. The overlapping space is the solution to the system. And that is it for this topic.